Hi friends, in this video I'll tell you how to calculate the potential due to system of charges. We'll start right away. Say if you have multiple charges here, Q1, Q2, Q3 and something like that. Now I want to calculate the potential due to all these charges at a point P, which is here. So if this is the R1 be the distance between Q1 and this required point P. So my potential due to the charge Q1 alone at this point P will be, as I said, KQ by R, that is KQ1 by R1. Now similarly, if R2 is the distance between charge Q2 and P, then my potential V2 at the point P due to the charge Q2 alone will be KQ2 by R2. Similarly for charges Q3 and Q4 as well. Now if I want to calculate the total potential due to all these charges at point P, it will be V1 plus V2 plus V3 plus V4. I mean it will just be the algebraic sum of all the individual potentials, and that's it. But this is okay for discrete charges, but if you have some continuous charge distribution, say what you have to do, say it has some volume charge density rho. So take a small element, say take a small volume element. The charge dq on this volume element will be rho into dv, where dv is the volume of that small volume element. So if I want to calculate the potential at point P, first I'll calculate the potential due to this volume element, and similarly I'll do for all these volume elements. Strictly speaking, I have to integrate it, and finally I'll end up with the potential due to this whole abstract or non-proper, whatever you call it as, this thing, this charge distribution. Now say I have a uniformly charged spherical shell and I want to calculate the potential P here, which is outside this sphere. Now if the distance from the center of the sphere to this point is small r, the potential will be just like what we got when we are dealing with point charge. So it will be nothing but 1 by 4 pi epsilon naught Q, which is the total charge which is on the sphere, by R, and this is the potential when R is greater than the radius of the sphere. But observe this, inside all the points, at all the points inside the sphere, the potential will be constant, because as I said before, there is no electric field within the charged spherical shell. So at all these points the potential is constant, and it should be equal to the value which we have at this surface also. And we know that when the radius is when the distance from the center to the point which we are calculating is greater than or equal to the radius of sphere, then the potential will be this thing. So at the surface I can write the potential will be 1 by 4 pi epsilon naught Q, which is the charge of the entire sphere, by capital R, which is the radius of sphere. This is the potential at the surface, and this is also the potential at all the points inside the surface as well. Hope everything is clear till now. Let's move forward. Now I want to calculate the potential due to electric dipole, and say this is plus Q and this is minus Q. As usual, this is the center of dipole O, and I want to calculate the potential at this point P. Distance from the center of this dipole to the point P is R, and from the positive charge plus Q is R1, and negative charge is R2. Now I can use the same superposition principle and say that potential at this point P is nothing but KQ by R1 minus KQ by R2 as well. This is the potential due to the positive charge, and this is due to negative charge. Minus sign is because the charge is negative. Well, this holds, but I want to write it in simpler terms. Now what I'll do, take this triangle plus Q, P and O. There if I apply cosine rule or cos rule, I'll get something like this. R1 square is equal to R square plus A square minus 2AR cos theta. This is just by cos rule, and I'll write it in another terms. R1 square is equal to R square of 1 plus A square by R square minus 2A cos theta by R. Well, everything is fine till now. If I assume that R is very greater than A, I can neglect this term, right? So finally I'll get R square is equal to R square of R1 square is equal to R square of 1 minus 2A cos theta by R. Now similarly, if I do the similar thing for the other triangle OP and minus Q, just applying the cos rule and stuff, I'll get something like R2 square is equal to R square of 1 plus 2A cos theta by R. Well, everything is fine till now. Now I can rewrite this as I have two equations, one for R1 square and R2 square. I can rewrite them as 1 by R1 is equal to 1 by R of 1 minus 2A cos theta by R whole power 1 by 2, right? Now using binomial theorem and considering only terms which are up to the first order of A by R, I can approximate this as 1 by R into 1 plus A cos theta by R. Everything is fine till now. And similarly, I'll get 1 by RT is equal to 1 by R into 1 minus A by R cos theta. Now, the potential, in the first we calculate the potential, right? This thing, using superposition principle. Here, instead of 1 by R1 and 1 by R2, you can write these things, this one and the thing which you get for 1 by R2 as well. So you end up with 2QA cos theta by 4 pi epsilon naught R square, where R is the distance of the point P from the center of dipole, and you know that P is equal to 2QA, where P is the dipole. So I'll write this thing as P cos theta by 4 pi epsilon naught R square, and P cos theta in terms P cos theta even can further be written as dot product of dipole and radius vector. So finally I can write this potential as 1 by 4 pi epsilon naught this thing by R square, and let me write this also, when this all holds when only R is very greater than A, because we use this thing while proving all this. So finally this is the potential due to dipole. Hope everything is clear till now. And oh my god, I'm sorry, this is theta. You might be wondering what it is, and just rewind the video for 2 or 3 minutes, and if you want you can go through the proof again, and it doesn't matter even if you don't, just try to remember this formula, this final formula for the potential due to this dipole. This is a very cumbersome proof, even I don't like it. However, let's move further. Well, this is the question. Two charges, 3 to 10 power minus 8 coulomb, and this charge is minus 2 to 10 power minus 8 coulomb. They are located apart, which are separated by 15 centimeters, and I have to find a point on the line joining these two charges where the electric potential is 0. Now if I extend this line in both the directions, now I have three cases. I don't know whether the point which satisfies the given condition is to the left side of the positive charge or to the right side of the negative charge, or it is in between these two. Now what I know is that it can't be to the left of positive charge, because if it is somewhere here, Just look at this situation. The magnitude of this positive charge is more, and the distance of this point from the positive charge is lesser than the distance from the negative charge. So finally the magnitude of the potential shown by this positive charge will be greater, definitely. So there's no possibility that the potential is going to be zero anywhere to the left of this positive charge. So I'm left with two other cases. What if the point is somewhere here? Now I don't know what is this distance. Let this be A, let this be B, let AP be X. So PB will be 15 minus X. Now potential at P due to A will be this K into Q, which is 3 into 10 power minus 8 by X, and due to negative charge will be minus Q by the distance will be 15 minus X. Well, this should be equal to 0, and I can take out the constant and all these things as well. Actually X is in centimeters, so however it doesn't matter because this thing even is going to get cancelled. And finally my equation becomes 3 by x minus 2 by 15 minus x is equal to 0. You solve it, you will get x as 9. I mean x is 9 centimeters. Now if your point is somewhere to the right of this negative charge, somewhere here, P dash say, then follow the same procedure. Your final equation will be just a little different. 3 by x, where x is the distance from the point A to the point P dash, and the potential due to the negative charge will be something like this. After cancelling, no, here it will be x minus 15 because x is greater. Equate this to 0, solve this, you will get x as 45, I mean 45 centimeters. So at 2 points on the line joining these two charges, the potential is 0. One is x is equal to 9 and x is equal to 45. Since this distance is 15, the first point will be somewhere between these two charges and the other point will be somewhere after the negative charge. Hope everything is clear till now, and that's it for today. In the next video I'll be starting with equipotential surfaces, and probably I'll start how to calculate the potential energy, and keep watching. That's it.